In this video, we'll be going through the solution to the December 7th bicycle sharing exam. Now, if you've lived in a city, you're familiar with bike rental programs, which allow you to rent a bicycle, ride it around the city for a while, and then return it at a different rental location. So to start, I'll begin by reading through the project statement. Now remember, on your exam, they will most likely give this to you printed out. I'll skip over the general information for candidates because this is the same as all of the other exams. The business problem. ABC Bike Sharing Company provides locked bikes throughout the town. Users pick up a bike using an access code and leave it at their destination. ABC has asked you to develop a model to predict bike sharing usage. The company is interested in predicting the number of bike rentals in a given hour to help them with the distribution of bikes. I look at the footnote and see that the data is adapted from the bike sharing dataset contributed to the UCI machine learning repository. If you do a Google search, you'll find that there's a Kaggle competition called Bike Sharing Demand. If you look through some of those notebooks, you might get interesting ideas for data visualization or modeling. So I want to begin on task 1. This says, your assistant has cleaned and provided data. Select which variables should be treated as factor variables. Justify your selection. So to begin, let's load the library and then load the data. Change data type to factor variables as needed. Replace variable with the variable. Copy as needed. Okay. Data dictionary says you have these variables. Season. This is 1 to 4. So this is an integer. So let's look at a glimpse. So season is default as an integer. However, the season variable is left as numeric because seasons can be compared to one another. For example, spring comes after fall, which comes after summer. What about year? Well, how many different years are there? There are only 2 variables. So the year variable has only 2 values. If I left this as numeric, a GLM would fit a single coefficient, which would be multiplied by either 0 or 1. So this would have the same effect as if it was converted to a factor variable which had only 2 values. Yeah, I chose to convert this to a factor so that the base level will be the one with most observations. To do that, I will just say, let's go down to task 1 underneath here and then make the changes. So variable year is equal to as factor year. What about hour? Well, this is already an integer. So this goes from 0 to 23. Okay. Do I have to leave comments on the variables that are not changed? No, it just says select the ones that are treated as factors. So that's okay as numeric. Holiday is 0 not holiday or 1 holiday. I'll convert this to a factor also for the same reason as the year. For the same reason that year was. And then next up is weekday. Weekday, day of week, Sunday, Monday, Tuesday, Wednesday, etc., etc. I will, well, so weekdays will be significantly different on workdays as compared to weekends. And so I converted this to a factor. However, we already have a variable for weekday. Let's look at the count. Data.all and then count weekday. Alright, there's an equal distribution of records, so that's good. There's not, if there was an unequal distribution of records across weekdays, then I would simplify the factor levels. But yeah. Okay, next up is weather situation. So this says it is integer 1 to 3, clear or partly cloudy, mist, rain, or snow. So there's no clear order to these. Situation has no order. The values are clear. They are clear or partly cloudy, mist, or snow. Snow. So this was converted to a factor. What about temperature? That's clearly an integer. Humidity, that's a double. Wind speed, that's a double. Bikes per hour, that's the target variable. It's a count of bikes, that's an integer. So I'll run this, convert this all to factors, and then I need to set the factor variables to those, set the reference levels to those which have the most observations. So let's check. So first, if I do summary all, I'll see that these factors, like year, the base level is 0, which only has 8,644 records, but year 1 has more records. And so that's out of order. So I want to convert base level to be year 1. The way to do that is just to change these variables to the factors that I have year, holiday, weekday, weather situation. And then for each of these variables, okay, and now you can see the base level is that 1. For each of these factors, the base level was set to be the value which has the most observations. Convert the selected variable into factor variables. renaming and releveling the factors as needed. Do not change the number of levels. Okay. So ideally, I will also change the names of these so that it's more descriptive. So how do you do that? Well, you can look at these levels. So let's take an example. Let's look at levels of year. I see that this is 0 or 1. So I can just set these values equal to the appropriate values. So year 0 is 2011. That's just year 2011. Actually, this is 1 corresponds to 2012. This is year 2011. Okay. Let's look at levels of holiday. 0 or 1. So this is going to be holiday. Not holiday. Holiday. Let's look at levels for the next one. The next variable that we were looking at, which was weekday. Okay, so I have to figure out which weekday is 6. That's Saturday. So that's Saturday. And then 0 corresponds to Sunday. And then 1 is Monday. And then 2 is Tuesday. 3 is Wednesday. 4 is Thursday. 5 is Friday. Okay. And I need to just comment that out. Now I just want to look at the summary again. And perfect. Now that's very easy to read. Let's just put that into the Word document. And there's a glitch right now with RStudio and Word. So what I'm actually going to do is press Windows Shift S to take a screenshot, and then copy the output here, and then press Control V to paste. Now, this actually hasn't been tested on a Prometric computer. However, when you are at Prometric, you should just be able to copy this and then paste it into Word, because that's the way it's always worked in the past exams. Task 2, 3 points. Consider a new variable. Your assistant has informed you that a new Workday variable is available. The value of the Workday variable is 0 for weekends or holidays and 1 for non-holidays and weekdays. Describe one advantage and one disadvantage of including the Workday variable in your model. The data already contains weekdays as a factor, and so there is overlapping information with the Workday. This is essentially a simplified refactoring of the weekday. So there would be linear dependency problems if both variables were included at the same time. For GLMs, there would be a convergence issue because the determinant of the model matrix would be 0. Is there anything in the code that asks me to do things? No additional code is provided. Okay, so what exactly do I have to do? So that's one disadvantage. One advantage would be that it simplifies the factor levels. So one disadvantage is that there will be linear dependence. One advantage is that the reduced factor levels is that fewer coefficients would be used in the GLM. For tree-based models, there would be fewer factor levels. This would reduce the variance of the model and make it more difficult to overfit. Task 3. Write an overview of the data for your actuarial manager. Limit your response to one page. Include any visualizations. So this is worth 12 points. So the description of what you do is actually worth more than what you actually do. Okay. Let's go down to task 3. So let's just start by looking at the summary of the data to see how many observations there are. I should say, let's look at a glimpse of the data. So the data consists of 17,376 records and 9 variables that are related to the number of bicycles per hour. We are providing ABC Insurance Company with models which will be able to predict the number of rented bikes based on the season, year, hour, holiday, weekday, weather situation, temperature, humidity, and wind speed. Now, I'm only summarizing tasks 1 to 2. In task 1, I looked at whether a variable was a factor or numeric. So we saw that the data had already been cleaned, and so we performed an inspection of the data types. There are two ways in which variables can be read into R. The first, either as a factor as a numeric variable, or as a factor. Numeric variables occur or are used to describe numbers, sequential numbers, numeric numbers, or to measure the magnitude of a process. Factor variables have no ordering. We used our intuition regarding the data to categorize the year, holiday, and weather situation. How would you describe this? Well, we know that that the year, that the data can change over time. There were 2 years where, as the city develops, new bike rental locations are added, and other changes are made to the traffic patterns. For this reason, we decided to treat the data from 2011 separately or differently from that of 2012. On holidays, we expect that the number of riders will be different because people will not have to commute to their day jobs. The same is true for weekdays. Whether the data considers only 3 classes of weather situation: either clear, partly cloudy, mist, or rain and snow. And so our model will account for this. So in summary, we have all of the data necessary to take into account the the climate and outdoor environment around the bike rental program. So the project statement says to specifically describe the target and predictor variables, and we have done that. Then include one univariate variable analysis and one bivariate variable analysis. So bivariate analysis would be this weather situation on bikes per hour. For a univariate analysis, we need to look at a histogram. So let's just look at the wind speed. This has an interesting shape. The distribution, the wind speed values are, what do they represent? These are probably standardized, right? Normalized wind speed values divided by 67 are below. The wind speed distribution below shows that most days are not windy. This distribution is right skewed and has a max of 67, a mean. So these values were just divided by 67. So if I just take this, so the maximum will just be the maximum times 67. I'm sorry, the maximum would just be 67, right? But you can't just take the median and multiply the median times 0.67. The math would not work that way. However, you can take the mean and just multiply by 0.67. So if you just took 0.19 times 67, that has a mean wind speed of 12.73. A mean of 12.7. The graph below, the raw data values have been divided by the maximum 67. Yeah. Okay. The other items in the project statement were include key descriptive statistics, one or two visualizations that best indicate what is going on in the data. Yes, we have done that.
Task 4, select an interaction to consider for your model. Explain what an interaction is. Let's just write out the definition. An interaction is when the impact that a variable has on the target depends on another variable which is used in the model. Explain why you selected this interaction. Okay, so let's look at the code. Go down to task 4 here. No additional code is provided. Use task 3 code snippets to explore for interactions as appropriate. So I know that any interaction will need to be explained. So I'll just look at the data dictionary and see if I can think of anything that would be reasonable. For example, weather situation and weekday. I might notice that people like to commute to work on the bike only while it is nice weather. Or perhaps some people don't have a car and they commute all the time on a bike regardless of the weather, whereas other people may only commute during nice weather or only ride the bike if it's on the weekend. So I just come up with that hypothesis. And then how would I test that? Well, I need to look at a graph that shows the weather situation and weekday. And I got this graph just from the boxplot code template. And so this shows weather situation, either 1, 2, or 3, and then the weekday. So weather situation is 1 is clear or partially cloudy. So 1 and 2 are clear or misty, but then 3 is when there's rain. So if there's an interaction here, it means that the height of these bars will be different for the different categories. So here, when it's clear or cloudy, it looks like the highest bar is for like Tuesday. The second highest is Friday. But when it's rainy or snowy, the highest is actually on Friday. You can also look at the orange bar. So on clear or cloudy weather, the Saturdays are quite popular. However, when it's raining or snowing, Saturdays are very unpopular. So the graph below shows the interaction between the weather situation and the day of the week. The x-axis values of weather situation 1 and 2 are for clear or misty weather, whereas the far right set of box plots for weather situation 3 is for rainy or snowy weather. So the orange bar represents Saturdays, and when it is not raining or snowing, these are popular days for riding bikes, as can be seen by the vertical height of the bar. During rain or snow, however, Saturdays are the least popular day. This makes sense because most people do not work during the week, and therefore this represents leisure time, which they could choose to spend elsewhere if the weather is not nice. Next question. Include descriptive statistics and visualizations to support the reasoning in your report. Okay, so we should look at descriptive statistics. I could read the statistics off of this graph, but it would be more reliable if I had a way of actually looking at the statistics. And the way that you could do that is by taking data.all and then grouping by the two variables that are interacting, and then just look at the median bikes per hour. So if I do that, I see that when weather situation is 1, yeah, 1, so we're just looking at 1 or 2, the median bikes per hour is about 149. That's the center of this box. In comparison, during the weather situation is 1 or 2 on Saturdays. In comparison, during rain or snow, this is, so I need to find the value where weather situation is 3 is 57. Task 5, 9 points. Perform a k-means cluster analysis. Your assistant has provided code to perform k-means cluster analysis on temp and humidity. Describe k-means cluster analysis. So before even looking at the code, I can just start the description. K-means is an unsupervised learning algorithm which groups observations into clusters based on the Euclidean distance. The method begins by randomly assigning cluster centers to the numeric variables. Then for each of the points, the distances to the centers are computed using the distance formula. And the point is assigned to the cluster which is closest. Then the cluster centers are recomputed by taking the mean of each of the values in that cluster. This process is repeated until the cluster centers stop moving. There is a parameter called n dot tries. No, what is the parameter called again? Let's look. Okay, so here's the code. N start, that's what it's called. N start, which controls the number of times that the algorithm is run. If only a few tries, a few runs are used, then the result can converge to a local minimum of the within cluster deviance instead of the global minimum. And this results in unstable cluster assignments. So the code was set up to use 10 starting values. All right, and now what I see the code here says, the following is the analysis the assistant provided. Do not change this code. So this is using temperature and humidity. Okay, and then this is starting, this is running k-means with different values. So here are the plots, and here's the elbow plot. So k-means relies on the number of clusters to be specified in advance. The above graph shows the between cluster total sum of squares on the y-axis and the number of clusters on the x-axis. There is no obvious elbow in this graph, and so we choose the value of 3. This segments the data into 3 groups. And then I want to just copy. So there's the assignment when k is equal to 1, all clusters are in the same group. K is equal to 2. There are 2 clusters, so here's k is equal to 3. The graph on the left below shows this. Finally, it asks, recommend whether the new variable based on clustering should replace temp and humidity. Justify your recommendation based on the graphs and the potential implications for the predictive model. If you just look at these, does it look like these are distinct groups, or does it look like there's one giant blob of points? Clearly, it's the former. There's no distance between these different groups, no matter how many clusters you use. And that means that k-means is not adding any value to your model. If there was, distinct regions, like the green cluster was up here, the blue cluster was down here, the red cluster was over there, then that would mean that clustering would be appropriate. So I would just summarize that. Based on the graphs above, we do not recommend using the cluster variable because the groups are not distinct. If the clusters were adding predictive value, then there would be distinct regions of points for each of the colors. Red, yes. This is the same regardless of whether we choose 3 to 5 clusters. Yeah, and you can maybe note these points. Like, there are some interesting outliers. It is worth noting that there are several points where humidity is between -1 and -3, and temp is between -1 and 0, which appear to be outliers. It does not make physical sense that the humidity would be exactly the same on each of these days. And so we suggest looking into these points to see if there is an error in the data. And that's these points right here that I'm referring to.
Task 6, 7 points. Construct a decision tree. Your assistant has provided code to split the data into test and training sets. Run the code as provided by the assistant. Let's open up RStudio and then run the code. And here I can see that it splits the data, 70% training, 30% testing. So let's just describe this. The code is set to split the data into 70% training and 30% testing. We examine the mean bikes per hour in both the training and test sets, as well as the combined data, and saw that this is about 189. Next part, construct an unpruned regression tree. Do not change the code. So this is just using bikes per hour as the target variable. It's using all other variables. And it's setting the CP value to 0.01, and the min bucket is 20. So I'll just say the code, the default code for training the tree uses a low CP value, 0.001, a min bucket of 20. So the CP is the complexity parameter and controls the variance of the model. A lower CP indicates that the tree will have more branches and variables the minimum bucket is the minimum number observations which are allowed in a terminal node. If fewer than 20 observations are split, then the split off in a branch, then this branch becomes a terminal node. So the tree was far too complicated to be used for this problem. We wish to adjust the parameters so that the tree will be simpler. Your assistant has set up code to generate a decision tree on the training data and perform cost complexity pruning. Construct a pruned regression tree with 4 terminal nodes using the code provided. Describe for each split of the tree why the characteristics of each resulting node make sense as it relates to the drivers of bike usage. So let's prune this tree so that we only have 4 nodes. So this shows the complexity parameter. Let's describe what that is. In tuning the tree, first a deep tree with many branches is fit. Then a pruning algorithm is applied to create simpler subtrees which remove branches that do not result in the model error reduced by a factor of CP. I don't actually remember exactly what this is, so I want to look at this documentation, and it's in this function here. So I'll mouse over it and then press F1 for help, and then I can look at the CP, the complexity parameter. So any split that does not decrease the overall lack of fit by a factor of CP is not attempted. So let's try adjusting this. So prune the tree using the complexity parameter that will result in 4 leaves. So let's just try a higher value because it started out at 0.01. So let's increase that and then look at the tree. Oh, that looks better. That only has 3 nodes. So we need to make this a little bit more complicated by making the CP lower. That has 1, 2, 3, 4. Perfect. So we adjusted, we increased the CP to 0.05, which results in this tree, which has 4 terminal nodes. What was the other part of the question? Describe for each split in the tree why the characteristics of each resulting node make sense as it relates to the drivers of bike usage. So we interpret the above tree diagram beginning at the top and working downwards. First, the tree asks people if they have rented bikes from hour 1 to hour 6. Is the minimum hour 1, or is it I don't remember. Let's just look. So I just want to look at the summary of data train hour. See what the minimum value is. So it goes from 0 to 6. Yeah, from 0 to 23. From hour 0 to hour 6, which is the night and early midnight to early morning and early morning. Then, if a person rented a bike during this time, then let me rephrase that. The number of bikes rented during this time is constant, approximately at 29%. Now, what does that actually mean? The target is bikes per hour. The number of bikes rented per hour. — 0.29. So on average, less than one bike is rented. No. The number of bikes rented per hour during this time is approximately 32. That's the number right here. And this represents 29% of the records. If the bike is rented from hour 7 to hour 23, and if the temperature is below 0.45, but remember I have to convert that. So the way to convert T minus min over max minus min. So max minus min is 39 minus negative 9, so 39 plus 9, 48. So it's 48. So it's something over 48. So it's T plus 9 over 48 is equal to 0.45. So I have to do some algebra. Say it's 0.45 times 48 plus 9. And I have this text thing in the way, so it's actually hard to read that. What is that answer? It's 30.6. If the bike is rented from hour 7 to hour 23, and if the temp is below 36, then the predicted value is 167. Yeah, if the temp is above 30.6 at this stage of the tree, and if the year is whatever year 0 corresponds to, so 0 is 2011, then the predicted value 243, and 377 if the year is 2012. Okay, let's go back to the project statement. Was that everything that they asked? Yes. So we could go into more detail about what these nodes represent. Like this node is the people who are using the bike at the really early time. This is the people who use the bike during the day, but only if the temperature is below this 36. This could represent people who are commuting during working hours, only during warm weather. but prefer to drive or take a train during cold weather. It's also worth noting that this year variable does show up in the tree. Which indicates that the ABC bike sharing program is changing from year to year. In the decision tree, the variables higher up are more important. So this allows us to read out that hour more important than temp, which is more important than year. If year did not appear, then the bike rental program would be the same, would have been same in 2011 as it was in 2012. Task 7. This is worth 12 points. Explain what boosting does and why it might be considered for this business problem. So first, I want to know, is the purpose prediction the first? It is important to consider whether the business problem is to gain inference about the data or to make predictions without needing to understand the model. The project statement says ABC bike sharing company ABC is asked you to develop a model to predict bike usage. The project statement says that ABC is interested only in prediction. And so this allows for, gradient boosted trees, well as bagged trees. For this problem, we have a mix of numeric and categorical. The numeric variable, remember we were looking at from earlier in the exploratory analysis, this bikes per hour. The numeric variables have non-linear relationships with the target. Let's just say may have. And so boosted trees can pick this up or use these variables directly, as opposed to a linear model which requires manual transformations. The factor variables, there may be variable interactions. Let's just say, there are some correlations between the variables, such as temp and hour. If you go back and look at the correlation matrix, here, you just look for like, season and temperature. So temp and hour and temp, hour and humidity. Negative 0.27 and temperature and season 0.31. So when you have a linear model and you use correlated variables, the p-values for one of the correlated variables tends to be low. Whereas with a GBM, with boosted trees, the variables are used together in the model, although they are averaged or incorporated sequentially into different trees. For a single decision tree, variables are automatically selected out. Another way to say this is that for linear models, one of the assumptions is that the variables are linearly independent, meaning they're uncorrelated. Because one assumption variables are independent. The next task. Your assistant has provided code to run a boosted tree with 1,000 trees, shrinkage of 0.01 or 0.1, and depth of 4. And now it's training. The clock is ticking. Clock is ticking. On a Prometric computer, this might take even longer. So definitely don't make any changes unless they explicitly tell you to. Okay. So this says construct a booster tree with given parameters and shrinkage 0.01. Do not change the code. Okay. And then plot partial dependence. And then they do the same thing for a tree with the higher shrinkage. So they say, what do they ask you to do? Plot the partial dependence plot for each of the two most important factors when the shrinkage is 0.01. Okay, so for 0.01, there it is. Now we want to look at the variable importance. So sometimes when you look at this graph, the labels aren't aligned with all of the importance. So it's better to use this table. However, you may get an error if you're pasting this in. So the workaround that I'm going to use right now is to take a screenshot and put that in. When you're actually on the Prometric computer, you should just copy and paste the table itself. The table below shows the variable importance. This is a way of measuring which variables are predictive of the target. The value is always between 0 and 100, and a higher value means that in the rank ordering values represents their contributions to each of the trees used. This is taken as the sum, the average over all of the boosting iterations. So the two most important factors are year and weekday. And if I don't remember which of these are factors and which are numeric, I can just do data test and then glimpse and see, hour is an integer and temperature is a double. So year is actually an integer. So the two most important factors are weekday and season. No, these are actually integers. Oh, interesting. There are actually no factors in this model. So this is a bit of a glitch, because if you remember earlier on, we had to convert certain variables to factors. Yeah, so we converted year and holiday and weekday to factors. So that means if I look at this table, year and weekday are the two most important factors. Now they want you to look at the partial dependence plots. So here's year and weekday. And so this year value only takes on two values. So this really shouldn't be a line graph. This really should be a bar graph with two bars, one at 0 and one at 1. The partial dependence for year is below. Although the R is creating a line graph, a bar graph with two bars, one at 0 and one at 1, would be more appropriate. The partial dependence is the effect of the variable after integrating out all of the other variables in the model. This is done by considering all of the pairwise combinations of year 0 and year 1 with the other values in the training data, and then looking at the average of the number of bikes per hour. So this, the result agrees with what we saw from the single decision tree, because 2011 for a year equals 0 is lower than 2012. And now let's look at this one, weekday. So what we see here is whoops, trying to put the text above the graph just so that I can be consistent. There it is. No, let's make it smaller. Huh. There it is. There we go. The weekday PDP graph shows that weekends for Sunday, I believe that's what it is 0 Sunday. Yeah, 0 is Sunday. And weekday equals 1 for Saturdays. The graph, the weekday PDP graph below, let's just describe what partial dependence plot for year below. Okay. Saturday disagrees with our intuition because people who commute to work using rental bikes do not work during the weekends. So the average impact of weekday on the number. So let's just say for Monday through Friday, the number of bikes is approximately constant between I just can't see what that is. It's 190 and 200. Saturdays are more popular than Sundays. So still about 190 as compared to actually this shows that it's about 0. No, it's about 180 is right here. So this is 85, so this is like 170 as compared to like 190. Okay, run the tree with the given shrinkage parameters. Run the tree with the 2 given shrinkage parameters. Describe the differences in results and explain how the change in the shrinkage parameter causes the observed differences. So a GBM, gradient boosted tree, GBM, begin if iteratively or sequentially fits trees where each tree predicts. No, let's just make it simpler. Gradient boosted tree sequentially fits trees to predict the target. The algorithm begins by predicting the average of the response, average of the target, and then calculates the residuals as the differences between the value of y and the average of y. Then a second tree is fit to predict this residual. This process continues for 1,000 times. At each step, the predictions are updated using a weight, which, well, are updated so that larger residuals have more weight. The learning rate controls how quickly the predictions change with respect to the number of boosting iterations. So these two models use a high learning rate 0.1 and a low learning rate. But the same number of trees. That's obvious. So let's look at the results. So we want to compare the predictive power of the two trees here. So the first tree, which used a lower learning rate, has an error of 574. And actually that's on the training set, so we just care about the test error of 6062 on the test set, which is worse than the second tree, which has an error of 2356. And what type of error is this? Calculate the mean squared error. A mean squared error which is much better. So yeah, so for this reason we chose to use 0.01. So as the learning rate is lower, more trees are required. Yes, in general, a lower learning rate with, in general, the optimal method of tuning a GVM is to use early stopping, which sets a high number of trees, which sets a low learning rate and a high number of trees, which is, it just sets a low learning rate and then continues to add more trees until the error stops decreasing. That is out of scope of this project. Explain how a boosted decision tree can predict negative bike rentals in this business problem when a single decision tree cannot. A single decision tree partitions the feature space into rectangular regions and then makes predictions which are the average of training samples. Because the number of bikes is always positive, the averages will also be. Therefore, decision trees will only make positive predictions. A boosted tree, on the other hand, sequentially it makes predictions for the residuals. Therefore, if the tree overcompensates for a positive residual by subtracting from the prediction, the result can be negative. Task 8, 10 points. Compare distribution choices for a GLM. Your assistant has prepared code to fit two GLMs to the data without the interaction in cluster variables, using the Poisson gamma distributions, each with its canonical link function. Explain whether each choice for distribution and link function is reasonable for this data and business problem. Let's look at the code. So here I see that it's fitting the Poisson, and then below it's fitting the gamma. And this is using a log link function, and for the gamma distribution it's using an inverse. You might be wondering why. So you can always look at the documentation to refresh your memory by typing in $family to the console. And here you can see family objects provide a convenient way to specify the details of the model used by the function GLM. So it tells you the family and then the link. And these link defaults are the canonical link functions. Recall that the canonical link is the statistically convenient way of connecting the linking the mean of the response to the linear predictor or the systemic component in a GLM. So if you ever leave the link argument blank, R will assume that you want to use the canonical link function. So the target variable, so let's just talk about what the first model, the Poisson model, uses a log link function, which is the canonical for this family. The target is a counting value, and so this agrees with the Poisson distribution choice. The log link has the added benefit of being easy to interpret because the multi-model can be translated into a product of relativities. In addition, well, let's just say the added benefits of being easy to interpret, because the model can be translated into a product of relativities, and being able to interpret the coefficients, values of the coefficients as having a percentage change impact on the target. The mean will always be positive because the inverse of a log is the exponential function, which has a positive range. And then let's consider the choice of gamma. Recall that a gamma distribution is continuous and strictly positive. The target variable is discrete. However, for large values, for variables, for target variables which span a wide range of numbers, using a continuous distribution is acceptable, because the results are approximately the same. You can think of this as if you have a histogram with only a few bins, that will be like a discrete distribution. Whereas if you had a histogram that had a lot of really small bins, as the number of bins went to infinity, that would become a continuous distribution. The link function of inverse is reasonable because this is the canonical link for a gamma distribution. One disadvantage is that there is a possibility for negative predicted values, because the inverse mean function has negative numbers in the range. We can also say the inverse function is monotonic, which means that we can interpret the signs of the coefficients as either increasing or decreasing the predictions. Now let's actually run the two models. And remember that the purpose here is to make a predictive model. So we're really interested in the performance. The interpretability is not as important. So explain the interaction. To evaluate the interaction, okay, your assistant set up code using the Poisson distribution with log link function. Well, let's just first look at the test set. Why do they give us the performance if they don't ask us to look for it? Okay, do each of the following for both models. The one with the Poisson distribution and the one with the gamma distribution. Okay, fit the GLM using the given distribution and canonical link function on the training data without the interactions or the cluster variable. Then run the summary function for the model and include the summary in your report. Okay, so let's do that. So we just need the summary function here. Let's make a heading. So I press Control B to turn on bold. And then go down to here and say gamma with inverse link.
Explain what information the model provides regarding the effect of being in summer as compared to winter. Let's look at the coefficients. But first, ask yourself a simple question. Do you expect that more people would ride their bike in the summer when it is nice and warm, or in the winter when it's snowy and rainy and cold? Obviously, the summer. That means that the coefficient in the model should be positive for summer. Let's check. We'll put this into an Excel file so that we can do some simple math. Remember that the season variables are going to be numeric by default. If you change them to be factor variables and then change the name to the name of the season in the first task, that would help you out in the interpretation section. If you didn't get to it at this point, that's perfectly fine. You can do it now. However, as a first step, you should check that your factor levels are correctly set to the base levels. This is really something that should have been done initially, but it's always good to have a second check when you're building the GLM. The way to do that is to look at the summary for the variable that you want. So if I look at summary data train, I'll see that the first value is the one that has the most observations. If this wasn't the case, you could just use this snippet of code. Data train is equal to data train mutate if is factor, and then factor in frequency. Or you could go back and copy and paste from the code snippets which do this for you. Now that we've gotten that out of the way, let's just look at the two predicted means. So we'll have season, we'll have summer and winter. Now for a GLM, we need to take the inverse of the link function. And we have a log link, so we just take exponent equals exponent of the intercept term. That's the overall average, and that's 105. And then for winter, we take the exponent of the intercept term, beta 0, plus the coefficient for winter, which is negative 4.9, times 1. And so that's 100. Let's do this. So you can see here that the delta is negative. In other words, there are about 5 fewer bicycles in the winter than in the summer. Let's do the same for the other model. So this used an inverse link function. So we're going to need to take the inverse of the inverse function. Let's copy this. Now, if you take the reciprocal of a number, like let's say 1 over 2, you get 1/2. Well, what happens if you take the reciprocal of 1/2? That's 1 divided by 0.5, which is 2. So the inverse function is its own inverse, in other words. So to take the inverse this, instead of taking the exponent, we're just going to take 1 over that number. So to begin, we take 1 over the intercept, and then we're going to take 1 over the linear predictor. So that's the intercept plus beta times x. And let's reformat this as a number because we're not scientists. Okay, so once we do that, we can see that the difference here is negative 12. Let's just round these. So this is the Poisson with log link, and then gamma with inverse link. And this table isn't, there it is. So let's just summarize. So to measure the effect that season has on the number of bikes, we look at the mean value, and then change the coefficients to be from summer is the intercept to winter. Before beginning, I checked that the intercept term is for summer is I checked that the base level is summer, so that the is summer because this has the most observations. So the overall average number of bikes for the first model is about 105, and then 100 in the winter. The second model makes an overall of 109 and then 97 in the winter. There's some weird formatting going on here, so let's fix this. Yeah. And then just say this makes intuitive sense because during warmer weather, we expect that more people will ride their bikes than in cold weather. And let's just talk about the inverse link functions. Then we apply the inverse link function, which is the exponent in the first model and the inverse in the second model. This converts the linear predictor to the mean to the predicted response. And this last bullet is explain what information the model provides regarding the effect of temperatures of 10 degrees Celsius compared to 20 degrees Celsius. Let's go back to our spreadsheet and look at the temperature variable. So we'll have 10 degrees Celsius. So let's do mean predictions, mean of Poisson with at 10 degrees 10C, and then mean of Poisson at 20. So we know already that we're going to be taking the exponent of the intercept, and then we're going to be adding something times 10. And this something is going to be, well, let's be careful here. We're going to be multiplying something times the temperature coefficient, except we don't know exactly what that is going to be. So let's just leave this as a number. Let's leave this times this space here, because we'll have to convert this to a number. So let's say this is 10 degrees C to coefficient, because why do we need to do that? Well, let's remember that temperature is normalized, right? So 10 degrees C is actually not is the numeric value of the temperature, but the value in the model in the data is T minus 9 divided by 39 plus 9. So this, let's just make a table that says temp and then normalized temp. So the temp is going to be 10 degrees and then 20 degrees, and the normalized temp is equal to T plus 9 divided by max minus min, 39 plus 9, or about 0.4, right? So in other words, instead of using the value of 10, we want to use this 0.39, right? And then remember that, whoops, we just do the same for this next value, except we use the value for temp 20. So let's just clean this up. To measure the temp impact, we first converted the temperatures values to be on the same scale as the normalized values in the model. Then we applied the inverse link to the linear predictors. So this is for the Poisson model. Now let's add some space so that we can do the same for the other model. Mean of gamma at 10C, mean of gamma at 20C. So here we want to take 1 divided by the linear predictor for the gamma model. So that's down here. So first we take the intercept, and then we add to it the temp coefficient times the normalized temperature value. And then we have to do the same for this one. 1 divided by the intercept plus temp coefficient times normalized temp value. And there we have it. So what does this actually say? Well, these are very different. Notice that for the Poisson model, that the temperature for 20 degrees is a lot lower, meaning that when it's cold, when it's warmer, the temperature is higher, then you have fewer bikes, right? But this seems very drastic, going from 222 to 60. Can that be right? Let's double check. So we're using the intercept, and we're using that. No, this is not right. That is right. Okay, this makes more sense. Yep. So that's a good example of when you see a number that looks off, question it. Let's just check the other values too. This is using 1 divided by the intercept plus temp coefficient times normalized temp. Yep. This one's using 1 divided by intercept plus temp times temp. Okay. So you can see that in both cases, when the temperature is higher, there are more bikes. Both models, when the temperature is higher, there are more predicted bicycles. Yeah, so this agrees with our exploratory results. In the first case, in the Poisson model, we use the exponential function, and we use the inverse function in the gamma model. Task 9. This is only 6 points. Evaluate the interaction term. Explain why the interaction term was not needed when fitting a decision tree. Well, the decision trees automatically capture interaction effects. And so we do not need to to specify this as we do with GLMs. The tree algorithm recursively splits the data using different yes or no questions. And each question can be understood as either increasing or decreasing the running total for the predicted value. So for an interaction is when a variable has a different impact on the target depending on the values of other variables in the model, which in the case of a tree is just the variables which are higher up in the tree. For example, if variable A were interacting with a variable B, then there would be two splits. There would be first a split based on A, and then for each of these values of A, the variable B would have a different impact on the predicted number of bikes. To evaluate the interaction, your assistant has set up code using the Poisson distribution with log link function. Run the code to fit the two GLMs with this setup, one without an interaction term and one with the interaction term selected in task 4. So fit the GLM without the interaction term. Do not change this code. Okay, and I'm assuming that they'll want us to put this output into our paper. And again, I need to take a screenshot instead of copying the text, which you should not have to do on the real exam. And then next, it says fit the GLM with the interaction term. And so construct the GLM with all original variables, but adding interaction. Using a Poisson distribution, replace variable 1 and variable 2 with the appropriate variable names. So run the code to fit two GLMs, one without the interaction term and one with the interaction term from task 4. So let's go back up to task 4. You might get a different answer at this point, depending on your choice for task 4. So we used weekday and weather situation. And it looks like all of these p-values are small, which means that the interaction terms are significant. That's exactly what we expect. We already knew this just by looking at the graph. Now it's just to confirm that the model's more predictive by looking at the AIC and the MSE values. So this is the model, and this is the model with the interaction. So remember, higher AIC is better. So this is AIC is 1231675 or 1.2 million, 1.2 million. And this one is 1.2 is 1229324, or let's just put them side by side so that we can see. So you can see that this first model without the interaction is actually higher. So without interaction, with interaction. So higher AIC is better. So the first model is better. Let's look at the RMSE. First one on the test set is 200,021, and the second one is lower. So RMSE, MSE without. Oh, that's obvious. Now, you might ask yourself, why is this the case? We compare the performance for each based on the penalized log likelihood and the mean squared error. The AIC takes into consideration the number of parameters, where a higher number of parameters is penalized. This is higher for the more parsimonious model. The one without the extra interaction coefficients. The MSE on the test set, however, is lower, better with the interaction. Okay, now what was the question asking? Recommend whether the interaction term should be included in your GLM model. Justify your recommendation. Now this depends on what the goal of the project is. So because the goal of this project is to maximize predictive power, is to make predictions for the number of bike rentals, we recommend going with the interaction. We recommend using the interaction because this result is based on the out of training and the external. Yeah, result is based on the test data set, which will be representative of new bike rentals, whereas the AIC is based on the training data. In addition, although adding the extra coefficients will make the result more difficult to interpret, this is not the priority of the model. Inference is not the priority of the model. Task 10. This is only 4 points. Evaluate the cluster variable in the GLM. To evaluate the cluster variable, your assistant set up code similar to task 9, but where the cluster variable is included. The variables producing the cluster variable are excluded, and the interaction term is excluded. Run the code to fit the GLM with the cluster variable. So we just have to run the code here. So this is construct a GLM with all variables in Poisson distribution on cluster data. Cluster data includes the cluster variable and excludes the variables used to create the cluster variable. Okay, let's grab this and put this into the report. We ran the code that used the cluster and excluded the variables used in clustering. Again, I have to take a screenshot. Okay, and then run the summary function of this model, include the summary in your report. Recommend whether the cluster variable should be included in your GLM in place of the variables that produced it. Justify your recommendations. So notice that this doesn't have the interaction term, and it doesn't say to add the interaction term. So all that I should be doing is looking at the MSE and the AIC and then comparing that to the one that was earlier. So test MSE is 2877, 2877. And so let's just go back up to our other GLM model without interaction. Or was this? Right. So this was our log Poisson model. So this is results with cluster, results without cluster from prior tasks. So you can see that the AIC is 1291956. So remember, we're just purely looking at the predictive power. We are purely looking at the predictive power when we decide whether to use the cluster variable or to use the original variables instead. So we see that the MSE is higher. The predictive performance is worse, and so we recommend not using the cluster. The MSE is higher, and the AIC is also higher, is lower. You can specify that higher is worse, and for AIC, lower is worse. Let's see, is that the only other part? Yes. In order to help our client to recreate this result, we need to give them the hyperparameters for the model. For the GBM are below: shrinkage of 0.1, entries 1000, interaction depth of 4, response family or distribution of Gaussian, so that the results can be reproduced. To help the client understand the value of your recommendation, do the following analysis and explain in terms the client will understand. Fit an intercept-only GLM using the code provided and include the summary in the report. So if we go down to task 11, we'll see that they have this code to do this for us. So to help you understand, to help us better appreciate how much value the GBM is added, consider what would happen if we did not use the data at all and instead predicted the overall average. You know, a metric such as mean squared error is not easy, does not have an intuitive explanation, because the value changes depending on the scale of the target variable. You know, this is yeah. So if we used an intercept-only model, we would be predicting that the mean bikes per hour would always be the average value. This results in a test MSE of right here, 3, et cetera, 33,546 bikes per hour. This is much higher than the GBM of only 2,356. Notice that also that when we add in the data and use the GLM with all of the variables, the MSE decreases by about 13,000. So the last point is explain how your model represents an improvement over using a model without any predictors. That is just an intercept term. And that is what we have done. We should also go ahead and include the output for the intercept-only model just so that they can compare the results to the prior GLMs that we had. We can also look at the summary output for this model as below. Yeah, and so that shows you like the median and the mid and the max residual. It might be worth noting that the median residual is negative. So notice that the median residual is negative. And if a residual is the actual minus the predicted, so the residuals are always negative, or on average they're negative, then that means that the predicted value is too high, that the predictions are too high on average. This makes sense because the distribution of bikes per hour is right skewed. If we take the intercept, notice that this is using a log link function. So if we use the inverse, so this model makes a constant prediction of e to the power of 5.24 bikes per hour. And what is that equal to? Exponent of 5.24. That is 188.7. Now notice what is the mean bikes per hour? That's equal to 189. So notice that this is the mean from the training data set. If you were to look at the mean for the, this is basically just a little bit different because the rounding error is because I rounded the value of the coefficient. So let's just clean up this wording. To help us better appreciate how much value the GBM is adding, consider what would happen if we did not use the data at all and instead predicted the overall average. A metric such as mean squared error does not have an intuitive explanation because the value changes depending on the value of the target variable. If we use an intercept-only model, we would be predicting the mean bikes per hour of e to the 2.4 is equal to 189, which is the mean bikes per hour of the training data. Task 12, 20 points. Write an executive summary for the client. Notice that the audience here is not the exam grading team, it's the client. Keep that in mind and always try to picture them, that high-level executive wearing a suit, and you're in a boardroom with 20 other people, your chief actuaries there. You're like the lowest level person in the room. How would you describe your analysis? So that in mind, just try to think about what are they asking? So they're saying your executive summary should reflect the information provided and work from previous tasks as relevant to the business problem. Your executive summary should include a problem statement, discussion of the data, a coherent explanation and justification of the recommended model, and conclusions. You may include any particularly relevant visualizations to supplement your writing. Your executives are interested in the value added by your model. Explain what your model adds to analysis of the business problem. Okay, so just structurally, it's a good idea to just break up your summary into two sections. So you could do, data. The first section would be data, and the second section would be modeling, our recommended model. So the first part maybe it's not going to be data. It's going to be, so now just try to be a little bit creative. Use more of the left part of your brain as opposed to the right side of your brain. When you write this, you can split your windows. So go up to the View tab, and then you click here, and then click Split. And then you can scroll up if you want to reference like an earlier part of your report. But be careful not to just copy and paste from what you wrote earlier. So let's take this bottom part and go down. And let's just summarize the business problem. So we could say, just say to ABC bike rentals from actuarial analyst. Remember not to use your actual name on this report because your grades have to be anonymous. So ABC rentals, so we present, and I'm using we because I think it sounds more professional. We present, let's just say actuarial analytics team because it's plural. We present you with a predictive analytics based solution to your problem of managing bike rentals. So using data and machine learning based results, you can efficiently predict what the demand for bike rentals will be, and then plan ahead accordingly. So the data. Let's talk about the data. I always like to talk about the sample size because the sample size tells you how credible your result is. This is also something that anyone can understand. So we use our results are reliable because they are based on 1,376 observations of bike rentals. Now, you can look in the project statement to see if you can get other info about the data source. You can see that this is actually in a footnote. So it was from 2013, and it looks like it was in California. In California from 2013. And then the variables that we looked at, the data set shows the season, year, hour, holiday, weekday, weather situation, temperature, humidity, wind speed, and wind speed, along with the number of bikes which were rented during number of bikes rented per hour. And remember that we did some analysis. We conducted cleaning and exploration and only needed to and made only minimal changes to the original data. All of these steps you can reproduce by following our easy to read documentation in the body of this report. So, and just say, our main priority, we understood that your main priority was to build a model, is to have a model that will be reliable for making predictions in the real world. To that end, we used blind holdout test where 30% of the data was used as a validation, which proves that our results are consistent. Our results will perform similarly when you deploy them. The model, So our recommended model, what is it? There is great news. There is tremendous richness to the data which you provided. And this allows us to build a highly accurate machine learning model. After looking at dozens of candidates, cleaning and manipulating, we found that the highest value model is a boosted tree ensemble. This had better performance than how many other candidates? Well, remember we looked at we looked at 1, 2, 3, 4, 5, 6. 6 other models. A GBM, this type of model known as a GBM, sequentially learns from the data by making iterative improvements. Out of all of the models tested, it is the most complicated. However, we do provide interpretations to the best methods possible, using the best methods possible. We are happy to discuss with you the other types of models which we tested. The first was a single decision tree. This has the advantage of breaking up the problem into a series of simple yes/no questions, but has the disadvantage of not making reliable or accurate, dependable, and we tested two versions of boosted trees. These are based on many decision trees which are connected to make a single model. On the other hand, moving to linear-based models, we tested 4 different generalized GOMs. These are a way of relating multiple input variables to the number of bikes per hour using a simple spreadsheet formula. Yeah, so we're talking about, the types of models that we tested, so you can really be consistent that you can be confident that these results are the best achievable, that can be achieved by comparing the improvement over not using a model at all. Let's go down to our intercept only model. So if we did that, the mean squared error, in other words, the average squared error, would be this number, 32,000, but they're not going to really know what that is. One way to enhance the credibility of your result is to tell the client what they already know. We can do that by looking at our observations of the data and stating what we've discovered. So after looking at your data, we found that, let's just go through and look. We found that most days are calm and not windy. That's okay. We found that poor weather makes riding bikes hazardous. Most days are, I really like to use bullet points here because otherwise it's so hard to put these sentences together. Most days are calm with little wind. People are half as likely to rent a bike during winter than during spring or summer. Actually, the mean number of bikes during rain or snow. That we found that riders prioritize comfort as well as safety because rentals were lower during cold or hot weather, hot temperatures. And we can also talk about an interaction, except we'll just say there's a relationship. There is a relationship between the day of the week and the weather situation because during work weeks, commuters have no choice but to ride a bike to their work, whereas on weekends when their rental is for leisure, rentals are far lower during poor weather. By looking at this decision tree, we can get an understanding of how the data is being split. So we could say that during early morning before 7, right? Because that's when it's before 7 a.m. The predicted mean is much lower. The number of rentals is quite low. When the temperature is less than, during the day, when the temp is below, this is remember the converted value of 0.45. So if you want to convert that back, you have to take 0.45. Oh, let's just go back to our tree. I think we talked about this. The temperature is below 30.6 degrees. So then the predicted mean is 167. The temperature is below 60. The number tells is lower, is moderate. The demand increases for higher temperatures, for warmer temperatures, and then finally, year 0 rentals. The program is growing in 2011 as compared to 2012. Let me just make sense. Let's just check this. So year 0 is 2011. Okay, I think that's enough. That is enough observations. And I'll just go through and fix some of these errors. Okay, and then we'll talk about the different types of model. Now let's do some interpretation of the tree. So here's our importance. Really, we should put this into the report, but we need to make a table in Excel. So let's just go grab that. And this will take a minute to run because it has to retrain the model. Yeah, this is really, really quite irritating that it is not allowing me to paste the results of the importance. So hopefully when you are working on this, you don't have this problem. So I'll just fix this quickly. Temp, hour, temp, weekday, year, season, humidity, weather situation, wind speed. Okay, so here's the variable importance, and I'll just clean this up. The model is not a black box because we can see that the variable importance agrees with our intuition. The most important variable factor is the time, because no person rents bikes during the night. The second is the temperature, as we saw, which makes sense, followed by the weekday. The ranking below is based on the GBM variable importance. This looks across each of the decision trees used and sums up the importance, the contributions, the gains, the influence from each tree, and then ranks them using a scale from 0 to 100. A higher value of predictive influence means that the variable was more than other variables used in the model. Okay? And we can also look at the partial dependence. Just be sure to use the same result from tree 2 because this is the model that had higher performance. So let's look at, for instance, hour. So here's the partial dependence for the hour. Now, you might wonder, which partial dependent plot should I look at? Well, why not look at the variable that is the most importance, which is hour? Then next, we can also look at the temperature. During mornings, when people are commuting to work, during the evenings, around 5 p.m., bike rentals are at a peak. The graph below shows the partial dependence, which is the effect that hour is having on the model. when averaging out the effects of the other variables. Let's also look at temp. The temperature, when the temperature is highest, is low, and cold. The weather is cold. People are less inclined to ride bikes. The demand gradually increases with the temperature, only up to a point, because people dislike weather which is too hot, as well as weather which is too cold. Now, we really want to drive home the fact that this model has the highest predictive power out of any other. And we can show that this will lead to better predictions by looking at the errors. Now, so one way to do that would be to look at the mean squared error. But another metric that's easier to understand is the mean absolute error. This is just the average size of the residuals. You don't need to know any simple or any complicated R programming, but you just need to remember that mean absolute error is the mean of the absolute value of the error, or the mean of the sum of the absolute value of y minus y hat, right? And so if you just take this little formula and you change this to be, the model's predictions, you can calculate the MAE. So let's take the MAE. So this is going to be the MAE for intercept only. So our prediction is y hat, and our y is data test bikes per hour, right? So if we do that, if we take the mean of the absolute value of the actual minus the predicted, we get value of 142. Now, if we do that for the GBM, let's go up to that. I forget what it's called. So tree2, predict trees, predict GBM2. Okay, so we calculate this. So just call this something like GBM pred is equal to that. And we take the absolute sum, the mean of the absolute value of that. We get a value of 38. So, compare this. So that's phenomenal. So yeah, so you can measure, we measured the value added by the model by comparing our model against a naive model. So the overall average number of bikes rented per hour is 189. If we made this prediction to every single bike that was rented, the average difference between the actual number of bikes rented and this estimate would be whatever this is, 140 something, 142, 143. By using our model, this error is significantly reduced to 39. I think that's good enough. Okay, at this point, it's time to start wrapping up by writing the concluding paragraph. This will typically include data limitations or possible research considerations. So some things to think about are the future availability. That's not really relevant to this problem because we know that the bike rental program is basically going to stay the same. Nothing's changing. The stability, well, we don't see that the temperature, humidity, these are very easy attributes to collect. And so there's not really an issue with data stability in this problem. There are definitely no racial or ethical concerns, and there's no data that's inexplicable. So most of these considerations are not a problem. And so we should focus instead on the business implications. How could they use this model in order to add value to their customers? So say in conclusion, ABC can plan ahead, can increase customer satisfaction and drive revenue growth by making more bikes available when people need them during off hours at night. We recommend performing servicing of bikes and moving bikes from populated areas to the areas to the rental locations, which will be used the following morning. Now, really just try to put yourself in the shoes if you're riding a bike around in a city. You would also be concerned about safety. Safety should be a priority whenever dealing with pedestrian and city data, because of the potential, lawsuits and because of the potential lawsuits. We don't want to institute changes to your program that would, result in increased risk for your customers. So this analysis did not consider, traffic accidents, riding accidents, or health concerns, or road hazards. And it may be worthwhile to consider these factors by looking at hospital admission or ER visits from rentals, from accidents, or road blockages from construction, or road blockages from construction. Rider satisfaction can be enhanced by servicing the bikes well to ensure that the air in the tires is always at optimal, is kept, and that the chains are lubricated. And the predictions, the demand for rentals could be tied to individual bikes, so that maintenance teams could track which bikes were due for servicing. And at this point, all of the writing has been done, all of the code has been written, and the last step is to go back and polish out all of the answers to really get the highest caliber writing and presentation throughout the report. So I'll go up to my view and I'll remove this split, and then go back. I'll press Control Home to go up to the top of the document, and I just want to look for any highlighted grammar changes. Right here, I'll just right click and then change this. And when I'm talking about a variable, it can often cause grammatical errors, or what appear to be grammatical errors, when in reality they're not. And so you can remove this ambiguity by making their variable names bold. You could also use like an underline or something else, but the method that the SOA solution used in this exam was to just use the bold typeface. So that's what I'll do. So I'm just going back through my document, and I'll do that. And yeah, I just noticed like there's a lot of like separate sentences. Yeah, and it's not going to be perfect. Like there's going to be some capitalization changes and things like that, but that's completely fine. And here I would just like to put this into bullets and then say like we performed as follows. You can also do things like highlight specific areas of your graph. You just go to the Insert tab, and then like if I want to insert a shape, whoops, I can do that. I can do Insert Shapes like this, and then get rid of the fill, and then make the outline like red, and put this over the left graph, because that's what I'm talking about for k is equal to 3.